thank you for the introduction, Ilya. And I'm going to talk about my result with my advisor, Shubhangi, who's in the audience. And it's on the problem of reconstructing depth 3 circuits with top fan in 3. So arithmetic circuits are what Robert described as algebraic circuits. So if you miss it, it's just is similar to Boolean circuits, but instead the gates have addition and do addition and multiplication, and the circuit computes a polynomial in the natural way, bottom up. And the problem we are going to talk about is reconstruction. And in this problem, you are given a polynomial f, which can be computed by a circuit C, which comes from a class script C. And you're given black box access to it. You can give it a point and you get what the evaluation of the polynomial on that particular point is. And your task is to efficiently output a circuit that computes the same polynomial as the circuit inside the black box. And if you add another restriction to it, that the output circuit should also be in the same class script C as the input circuit, this problem is called proper learning. And yeah, so this problem, if you look at depth 1 circuits, it's kind of trivial. It's just fitting, if it's a single gate, and it's just figuring out the coefficients. But as soon as you move to depth 2 circuits, the problem is no longer trivial. For example, if the circuit input to you is a pi sigma circuit, which basically means you have a top addition gate and a bunch of multiplication gates. Each multiplication gate is computing a monomial. So what you're computing is basically sum of monomials, or the dense representation of the polynomial. And the problem is equivalent to multivariate interpolation, which we do know how to do in polynomial time, thanks to Benoit Tevari and Clarence Spielman. But still, it's not trivial, even for depth 2 circuits. And if it's a pi sigma circuit, which is basically a multiplication gate, taking input a bunch of addition gates. Each addition gate is computing a linear form. And the problem basically becomes into factoring the polynomial in a black box setting. And we do know algorithms for this as well, thanks to Carl Toffen. And yeah, but even for depth 2 circuits, the problem is kind of non-trivial. But as soon as you move to depth 3 circuits, if it's like a pi sigma pi circuit, then just the combination of the two techniques we discussed work, because the polynomial is a multiplication of sparse factors. But if you look at a sigma pi sigma circuit, the problem becomes extremely challenging. And not just general sigma pi sigma circuits. If you look at reconstruction for a restriction of set multilinear circuits, it captures NP-hard problem, tensor decomposition. And the problem is interesting enough that I can give you an open problem on the earliest slide. And we don't know how to do proper learning for just sigma pi sigma circuits with top fan in 2. I will define what top fan in is, but just think of a very small depth 3 circuits over just 5 variables, and we don't know how to do proper learning for this. And to convince you more that the problem is kind of hard, yes?
Just take it back. By proper, we mean you want exactly top fan in 2.
Yes, yes.
You want like top fan in 3 with the portfolio.
No, I want exactly top fan in 2. Yes. So just to convince you that the problem is even more difficult for depth 3 circuits, we have depth reduction results, which basically show that any arithmetic circuit of poly size, you can basically shrink it to depth 3 with non-trivial blow up. And what it basically means is if you can do polytime reconstruction for just depth 3 circuits, you get sub-exponential reconstruction for general arithmetic circuits. And a closely related problem of pack learning, if we get polytime pack learning algorithms for sigma pi sigma circuits, Clivens and Shoto show that it breaks cryptographic primitives. So we don't even assume we can get polytime pack learning algorithms. And as I discussed, proper learning algorithms for set multilinear depth 3 circuits it captures tensor decomposition, and Johann Hastad showed that it is NP hard. So depth 3 circuits are like kind of difficult. So we look at a restriction of it, and this is how a depth 3 circuit looks like. The bottom layer is a bunch of addition gates. You have multiplication gates. Each multiplication gate is a multiplication of linear forms. And the way we will restrict is we will only have k multiplication gates, which all feed into the top addition gate. And we are basically restricting the fan-in of this circuit, and the polynomial f would be a sum of k terms. Each term is a multiplication of d linear forms with these are degree, and we'll call each of these the polynomials computed at each of these multiplication gates like t1 to tk. And yeah, we will be representing this sigma pi sigma circuit with top fan in k by this notation, and algebraic expression to write what we just discussed is you can write the circuit as what you can also do is take out the GCD of all these gates, which means you take out all the linear forms that happen to be in all the gates, and the remaining part you call it as the simple part of the circuit, and you ensure that the GCD of each of the gates is 1, and each of the gates is a product of linear form. So this is how the polynomial computed by the circuit kind of looks like. And one thing that is very important for our notations is the rank of the simple part of the circuit, which basically, whenever I say the rank of the circuit, I will mean the rank of the simple part, which basically means that so all these linear forms that happen to be in the simple part of the circuit, you can think of them as vectors, and then the vector space they define, the dimension of this vector space would be the rank of the simple part of the circuit. And this will be a very useful quantity for us, which we will see. So this is a kind of obvious restriction, but has these kind of circuits been studied before? And the answer is they have been studied for the problem Robert talked about, PIT, which is you're given a circuit and you have to check if it computes the zero polynomial or not. And it has a simple randomized solution due to Schwartz-Zippel lemma. Just pick a random point and check. And de-randomizing it is a big open problem, as Robert talked about. It should be noted that de-randomizing PIT is easier than trying to do deterministic reconstruction, because if you are learning the entire circuit, you know if it's zero or not. So PIT for these top depth 3 restricted top fancy circuits, these find connections to really interesting problems in discrete geometry, and specifically Céleste-Galaïc configurations. So a bunch of heavy words. So I will describe what it actually looks like. So think of a circuit with top fan in 3. Each gate is a product of linear forms. We'll say like T1 is a product of red linear forms, T2 is product of blue linear forms. Each point represents a linear form, and so on. So if I pick, let's say, 2 points, a red linear form, let's say L1, and a blue point, let's say L2, and if we consider a circuit mod L1, L2, since this circuit was computing an identity, it was computing 0. So 0 mod anything is 0. So, but when you go mod L1, L2, T1 and T2 vanish, because these linear forms happen to be in the product of them. So what you are left with is T3, which is a product of linear forms, vanishes mod L1, L2, which basically means by Bezos' theorem that there's a point that lies in the span of these 2 points. And this is a huge restriction, right? You pick any 2 different color points, and there must be a third colored point that lies in the span of these 2 points. And this problem is known as the colored high dimensional Sylvester-Garai problem and has been studied well enough. And what they basically show that if the set of points kind of follow these restrictions, then they all usually lie in a small dimension space. And using these kind of ideas, there was a long line of work which eventually gave black box polytime PIT algorithms when when the top Fanon is constant. And an idea that constantly appeared in these results was that if the depth 3 top Fanon K circuit is computing an identity, then it must be a low rank circuit. So the rank we defined is, for example, if the circuit is over reals, you can show that the rank of such a circuit computing 0 is at most 3k squared. And so it does not matter the number of variables, it does not matter the degree, the dimension, the space, the dimension of the space in which all these linear forms are lying, it has to be very small. And if k is a constant, they have to be in a constant dimensional space. So yeah, so this is a huge structural way of understanding about the computation that happens in depth 3 circuits. So we have known these structural results since 2013, but what do we know about reconstruction for these type of circuits? And so if the top Fanon is 1, this is just like when k is 1, this is just a pi sigma circuit, which we discussed. It's just factoring, and we know algorithms for. But as soon as you move to top Fanon 2, even though the problem is challenging, and even though like the PIT is kind of trivial because the two products cancel out only when they are the same, right? Because of unique factorization. But when your circuit looks like this, and the reconstruction is kind of difficult, because how do we even learn these linear forms that appear in this circuit even when you are just given black box access to it? So the problem is, it starts becoming challenging at top Fanon 2 and becomes more difficult as you increase it. But top Fanon 2 has been studied before. So in 2007, Amish Velka gave an algorithm for top Fanon 2 depth 3 circuits that worked for finite fields and had a quasi-poly running time. But interestingly, it had a dependence on the size of the field. So when we say finite field, it only means small finite fields. And even if you have large fields, this is an exponential running time. This was further generalized by Kaninch-Velka, where for any constant k, but the dependence for on the field size continued. And we will discuss why there's this kind of field dependence in these results. And more recently, Gaurav Sinha gave a polytime algorithm for top Fanon 2 in cases when the field is reals or complexes, and in 22 he gave another result which and did reconstruction in polytime when the field was larger but finite. So basically, depth 2 we know how to do in polytime. Top Fanon 2 we know how to do reconstruction in polytime. So what another thing is that all these reconstruction algorithms, they only do proper learning when the rank is high. If the rank is small, we don't know any proper learning algorithm. And the open problem I discussed, we don't know how to do reconstruction proper. Don't know how to do proper learning. So what we do, we show when the field is reals or complexes, and we have top Fanon 3. We give a randomized quasi-poly algorithm to do reconstruction for these kind of circuits. And our algorithm also does proper learning when for any ij, the rank of ti plus tj is at least some log D. So just think of it like any two gates at least differ on some log D log D independent linear forms. If it's far enough, we do proper learning, and in other cases we still output a circuit, but the fan-in is higher than 3. And this is the first sub-exponential time reconstruction algorithm that we know for the model of depth 3 top fan-in 3 circuits. So for the rest of the talk, I'm going to go through the basic proof idea of what we do. So our proof basically goes through 3 steps. The first step we do is we show a bunch of structural results about top fan-in 3 depth 3 circuits. Next, we give an algorithm to find a few linear forms that happen to be inside the circuit. And finally, we'll show how to learn the entire circuit from the few linear forms we learned. And let's talk about this third step because it mainly comes from work by Shvelka and Shvelka. So our goal right now is to learn the circuit from the few linear forms we have. And let's say we have a linear form. Someone gave us a linear form L1 that happens to be a factor of T1, right? So we have black box access to C, so we can get black box access to C mod L1, where the gate T1 will vanish, and we basically have access to T2 mod L1. And let's say instead of just L1, someone gave us L2 and basically log D independent linear forms. And by using the black box access to C, we have access to projections of T2 mod these log D independent linear forms. And what Shvelka showed that is that this is enough to learn T2 itself. Once you have learned T2, you can just subtract it, and then it's you get a top fan in one circuit, which you know how to do reconstruction for. And this result uses lower bounds for 2-query LDC codes, which is a very interesting use of the technique. And Khan and Shvelka generalize this technique to work for projections of top fan in K circuits, and therefore they get a algorithm to do reconstruction for when the top fan in is any constant. But the one question you have is like, where are these linear forms coming from, right? Where do we get them? And the way Shvelka and Khan and Shvelka do it is they find a variable reduction to log D independent linear forms, and then they brute force over all possible linear forms on these log D variables. So therefore, they have this field to the log D running time dependence. But you obviously cannot do this for reals or complexes. Where do we get our linear forms from? And we get it from something we'll be calling as vanishing spaces. What do I mean by that? Well, consider 3 linear forms of 3 different colors, L1, L2, L3. And what happens if I look at the circuit mod L1, L2, L3, mod the ideal generated by L1, L2, L3, each of the terms vanish because you have set a linear form in their product to 0. So the circuit vanishes when you mod this ideals, which basically means that this co-dimension 3 space, when you look the circuit over it, the circuit vanishes. And so let's say somehow you know this space. Let's say you have you take another blue or gray point, L2 prime, L3 prime. The circuit also vanishes over the L1, L2 prime and L3 prime. And somehow I have access to the list of all codimension 3 vanishing spaces for this circuit. Then I know these 2 spaces. And if I take the intersection of their kernels, I can learn L1, which was our goal. Our goal to learn linear forms that happen to be in our circuit. So all I need is this list, which we'll call S3, which is the set of all codimension 3 vanishing spaces. And the first question we have is this set even finite, right? So consider this. Not all points in T3 need to be green. They could be, let's say, purple. What that mean is if I took L1, L2 from, if I took L1, L2 from the two sets, let's say there's a linear form, which is just L1 plus L2, lies in the span of the two linear forms. Then to find the codimension 3 space, I set L1, L2 to 0, and the third linear form, I could choose anything. And that means, since we are over real and complexes, there are infinite such codimension 3 vanishing spaces. And similarly, you can do it for codimension 1 as well. So what you need to do is you need to define 3 sets of spaces, S1, S2, and S3, and you need to have maximal conditions. Basically, that when you are looking at S3, you have codimension 3 spaces, which are not contained in spaces inside S1 and S2. But we only talked about spaces where all the 3 gates vanish. But are those the only spaces that happen to be in our set? Well, consider this polynomial. It does look fancy, but it's just a top fan in 3 depth 3 circuit. It's just product of linear form, 3 linear forms in each gate. And what we are going to do, we are going to go mod x2 minus x3. So x2 minus x3 does not happen to be in any of the gates. So if I'm going mod this, none of the gates are going to vanish. Each of the gates remains a non-zero polynomial. But if you add them all up, it vanishes. Everything gets cancelled. So there could be these kind of linear forms which divide the circuit, but yeah, do not happen to be there. So this can happen for codimension 2 and codimension 3 spaces as well. And yeah, so what we first show, the step 1 of our proof, is showing that these spaces, the structural result I talked about is that these sets S1, S2, S3 are not only finite, they have polynomial size, and when the circuit is high rank. In the next step, we show that not only these are small in size, but we can compute these sets in polynomial time. The third step is, so we discussed how we can find linear forms from S3, but when we add these maximality conditions, we lose some of the spaces we might have required to learn linear forms. And step 3 is analysis, that we can basically learn log D independent linear forms using S1, S2, S3, even because of this loss. And step 4 is what we discussed, using the techniques of Shvelka and Kanin-Shvelka to reconstruct the circuits from the few linear forms we learned. So for the rest of the talk, we are going to only focus on our step 1, which is showing that S1, S2, S3 are finite. So for S1, if the circuit vanishes mod this linear form, what it means is that this linear form divides the circuit. Since the circuit computes a degree D polynomial, it can only have D factors. So S1 is at most D. So very simple to see. And we know much more about this space S1. And if you basically consider the set of linear forms that divide the simple part of the circuit, we know by results by Shvelka and then further used in paper by Shvelka and Kanin-Shvelka that that this set is small dimension and there could be only log D independent linear forms in it. This comes from the lower bound for 2 query locally decodable codes as well. So let me try to give you a brief overview of how we bound the set S2. Let's consider any 2 codimension 2 spaces over which the polynomial vanishes. The easy case is when some Ti vanishes over this codimension 2 space. What that means is that, let's say, Ti is T1 without loss of generality. And what means that there's a linear form L that divides T1, and it happens to be in the span of L1, L2. If you do a basis change for L1, L2, you can also have a linear form L prime such that L and L prime is a basis for the space. C mod L is not zero because of the maximality conditions. And what it basically means is that L prime divides a non-zero polynomial C mod L. And since L divided T1, we only have D choices for it. And C mod L is a non-zero degree D polynomial. L prime, we have D choices as well. And which means that we have only D square choices for VL1, L2. So the interesting case is when none of the gates are vanishing. And what it means is that you had a high rank circuit, you went mod this codimension to space, and now it became a low rank circuit. Why a low rank circuit? Because of these rank bounds we discussed for the PIT. And what it basically means is how when we mod L1, L2, none of the things vanished, but it still became low rank. And the way that can happen is these linear forms no longer continue to be in the simple part. They all became red and they moved into the GCD. And this means that these the space we had is contained in spaces of the linear forms that moved into the GCD. And if we fix a bunch of these linear forms, it kind of fixes the space that we wanted to talk about and kind of fixes the linear form. And another slide that the case where it's not 3-dimension spaces, in that case as well, you kind of restrict the circuit. And overall, all the S2 case, all the set of S2 spaces, you can show that in every case you have only poly D many such possibilities for these kind of spaces. And then S3 is just this even even more stronger analysis, but the same idea. And finally, I would like to talk about some future work, and the natural extension for the work is to do reconstruction for depth 3 top Fanon K circuits when K is greater than 3, and we have some ongoing work on it. But more interestingly, when the circuit has low rank, we don't have any proper learning algorithm. And I think that's a really simple circuit which we don't know how to do proper learning for. And it's a very easy to approach problem, but we have no idea how to work on it. So that's it. Thank you.